Hey there, Happy New Year. Well, we're at home another day, and we really do need to cover a little something. So I put together a little lesson on potential energy functions and curves for today. The good news is you can do it in your pajamas at home, so at your leisure. That's nice. But I do need you to watch this video by Wednesday, and then we'll do some problems in class on Wednesday to follow up on it. We talked about some of this before break, but it's been a while. You probably need a little bit of a refresher. So let's just go over the basics. So just to review, hopefully everyone knows what potential energy is, right? It's energy that's stored in an object. It's really stored in the force field. And it's the result of doing work against some sort of conservative force. And we've mostly focused on two conservative forces so far. We've talked about gravitational potential energy. Gravity is a conservative force, so when you do work against it, when you lift something, you give that object gravitational potential energy. And the formula for that, remember, is mgh. It's directly proportional to the height to which you've raised it. And when you stretch or compress a spring, you give that spring elastic potential energy because the force of a spring is another example of a conservative force. But there are other conservative forces too: magnetic forces, electrostatic forces. Forces between atoms and molecules can be conservative forces. Um, and there are other examples of, those all result in different potential energies. But we've mostly focused on the first two. When we start to work with potential energy curves, though, we might see some examples of some of those other types of potential energy. But the nice thing is that we don't really have to worry about what the situation is that resulted in that particular potential energy graph. We just have to know how to deal with the graph. So we'll talk about that. All right, so I do think we talked about this before break. There's a relationship, obviously, between force and potential energy, since potential energy results from work being done against a conservative force. There is a relationship there, and that is that the force is the negative of the derivative of potential energy with respect to position. Or another way of saying that is potential energy is the negative of the antiderivative of force with respect to position, right? So we can see that with the examples that we already know about. Gravity is mg down. Gravitational potential energy is mgh, right? So if you take the derivative of mgh and make it negative, you get negative mg. Similarly with Hooke's law, the force against a spring is F equals negative kx. Remember, the negative sign there just means that if I stretch the spring one way, it pulls back in the opposite direction. That's all that negative sign means. Those negative signs just have to do with direction. And the potential energy formula that's associated with that is the negative antiderivative, so 1/2 kx squared. All right, so equilibrium. We've used that word a little bit. We're going to use it in a slightly different but related way in this unit. And equilibrium is just when the force is zero, right? So we already kind of knew that, right? We talked about equilibrium as being when the net force on an object is zero when we did Newton's laws, for example. And since the force equals negative du dx, if the force is zero, that means du dx must be zero. And graphically, if the derivative is zero, that means it's a flat point on the graph, right? It's a place where the slope is zero on the graph. Might only be flat for, a very, very small interval, but it's a flat point on the graph. So, but as you know from calculus class, that can take many different forms, right? It can be the sort of the center of a concave up kind of parabola looking type curve, or it can be, that highest point on a concave down. So you would call these what? A relative min, right? And a relative max. Or you can just have a flat part of a curve, right? Just a horizontal portion of a curve. These would all be examples of equilibrium because these are all position or sorry, these are all potential energy on the y-axis versus position on the x-axis. So these are all different examples of equilibrium. These are all different ways that we can have a slope of zero. But they represent different situations, and we need to talk about that. So the one where it's concave up and we have a relative minimum, that's an example of stable equilibrium. When it's concave down and we have a relative maximum, that's what we call an unstable equilibrium. We'll talk about why in a second. And when it's flat like this, we call that neutral equilibrium. So let's just talk about what those are briefly. Stable equilibrium is when if you give the object a little push, you're going to, or a little displacement, a little movement, you're going to cause the potential energy to increase. And potential energy can't increase without drawing from some other pool of energy. So what ends up happening is that means the kinetic energy decreases. And that means the object slows down, and eventually it'll come to a stop, and then it'll come right back down to where it started. So think about a marble sitting in a bowl. If you give that marble a little push, it's going to go up the side of that bowl, and as it goes up the side of that bowl, gravity is going to start bringing it down. It's going to start acting against the direction of motion. It's going to come to a stop, and then gravity is going to bring it back down to the center again. And maybe it'll oscillate back and forth depending on how much energy you gave it over time. Of course, if this is a real bowl, it'll lose heat to friction or lose energy in the form of heat because of friction. But it'll stay in that general area. It won't go rushing out of the bowl for sure, as long as we give it a little push, not a huge push. Obviously, there is a push that will get it out of the bowl, and we'll talk about that eventually too. A mass attached to a spring would be another example of a stable equilibrium. So if you compress that spring or stretch that spring, assuming it was unstressed to begin with, it'll start to oscillate around that equilibrium position. In fact, we spend a whole chapter later talking about that motion. It's called simple harmonic motion. It's the one that mesmerized you so much in class when we had that hooked mass bobbing up and down at the end of that spring when we did the Hooke's Law lab. So anyways, stable equilibrium was when a little displacement causes the potential energy to go up. So again, if you think about this marble, if we give it a push, it rises up the side of the bowl, it increases its height. That means its potential energy increases, and that increase in potential energy comes from its kinetic energy, so it slows down, and then it'll come back down, and its potential energy will turn back into kinetic energy as it comes back down. Unstable equilibrium is the exact opposite. It's when a small displacement results in a decrease in potential energy, which means it's going to result in an increase in kinetic energy. So think about, instead of a marble inside a bowl, maybe think about a marble on an upturned bowl sitting on the top of the bowl. So that if you give it a little push in either direction, it's a very round bowl. It doesn't have any bottom to it, or just a hemisphere or whatever. So if you give it a little push in either direction, it's going to start rolling down, and as it rolls down the side of the hemisphere, it's going to pick up speed. It's not going to slow down and be brought back to where it was. It's going to race away from where it started, right? And thinking about that in terms of energy, a slight displacement means that it's going to go down, right? It's going to go downhill. So that's a decrease in potential energy, and that lost potential energy has converted into kinetic energy, so it's gaining speed in this case. And then neutral equilibrium is probably exactly what you would guess. It's when a small displacement doesn't really have much of an effect on the potential energy, neither an increase nor a decrease. So think about a marble sitting on a table. You give a little push, you haven't changed the potential energy. So, whatever kinetic energy you give the marble, it's going to maintain that kinetic energy, but it's not going to increase or decrease its kinetic energy the way it would in the other situations. So going back to the graphs again, so you can see that if you have an object in a stable equilibrium, remember these are graphs of potential energy versus position. Any displacement in either direction is going to cause an increase in the potential energy and therefore a decrease in kinetic, and it'll come back and it'll oscillate around. Even though this is a graph and not a physical thing, you can really think about this as like a marble on a track. And if you had a marble sitting right there in that little dip and you gave it a little push, it would just end up, as long as it was a small enough push, it would just end up oscillating back and forth. Whereas if you had a marble here in the unstable equilibrium situation, you give a little push, woo, boom. And here, you give the marble a little push, probably it'll come up here and roll down, and then maybe come back, and I don't know, kind of depends. Neutral equilibrium, honestly, it's not very interesting, so it doesn't come up very much. All right, so we have two potential energy curves associated with the conservative forces that we've been studying, but they're kind of boring, you know, gravity. As long as we're talking about gravity very near the Earth's surface so that it's a constant gravitational pull on an object, meaning like the object's weight doesn't change, we're just talking about a straight line potential energy graph, really. It's just MGH, right? So as H increases, the potential energy increases. Now, that being said, there is a more interesting potential energy curve associated with the force of gravity when you start talking about objects that can get really, really, really far apart, such that the force decreases as the distance between them increases. But we will talk about that more in a later chapter, so don't worry about that too much right now. So as far as we're concerned, as long as we're near the Earth's surface and the object's weight is a constant, which is all we've studied up till now, the potential energy versus position graph is just a diagonal line with a slope equal to the object's weight. Pretty boring stuff. No equilibrium points at all there. A spring is a little bit more interesting, right? It's 1/2 kx squared, so we've got a parabola going on here. We've got a point of equilibrium. Ask yourself, what type of equilibrium position is that? Hopefully you thought stable, and you're right. So if you give it a little push in either direction, the spring is, providing what's called a restoring force. It's going to bring the object back to that stable equilibrium point. And it might overshoot that equilibrium point and go over to this direction and oscillate back and forth, but it's not going to go, significantly further away. It's going to be brought back towards equilibrium. That's really when we talk about F equals negative kx for Hooke's law, that's what that negative sign means. It's a restoring force. You pull in one direction, you move the object in one direction, the spring pulls the object back in the opposite direction. It's always going to pull back towards equilibrium. We don't have any unstable or neutral equilibriums in this particular situation, though. And like I said, these are the only two forces that we really deal with a lot, but because they often want to give you more interesting potential energy curves to deal with, sometimes they'll give you things that we haven't studied. But you don't really need, like I said before, you don't really need to worry about what are the forces that cause these curves. You just need to deal with the curve itself. So here's a more interesting one. This is the potential, that's the potential energy in a van der Waals molecule. So think about like a dipole-dipole interaction, right? If you've got two atoms, if they get too close, really, really close, their electrons start repelling each other, right? So they repel each other. If they get really far away, however, with a dipole-dipole interaction, you're going to have an attraction. And so those two forces, you've got the short-range repulsion and the long-range attraction. At some point, those two forces cancel out, and there's a place between the two atoms, or, well, there's a separation distance between the two atoms where they won't be applying any net force to one another. And that is their equilibrium position. And I showed this graph because there's actually an old AP question that we'll do on Wednesday together that builds off of this idea. So there's a position, like I said, it's called RE here for, the equilibrium position, where that attraction and that repulsion are canceling each other out, and the net force is 0, and we have a stable equilibrium position. If they get any closer than that, if they get any closer together than that equilibrium position, then the atoms are going to start repelling each other. Their electrons are too close, and they're repelling each other. And if they get further away from that position, they start attracting each other. So they have this sort of ideal separation distance. And any change in that separation distance is going to cause a change in the potential energy. Here's another example. I pulled this off the web, and I'm not even sure it really is associated with anything physical. And this is often what they will do. They'll just give you a totally made up potential energy versus position graph and ask you to identify the equilibrium positions, for example. So go ahead really quickly and identify the various equilibrium positions in this graph. And also ask yourself, what kind of equilibrium position is it? Is it stable? Is it unstable? Is it neutral? Okay, so hopefully you did that. So we've got a few. We've got what looks to be a neutral equilibrium position here at x equals 0, right? Looks like it's flat up here. We've got a stable equilibrium position at x equals 2, an unstable equilibrium position at x equals 3, and another stable equilibrium position at x equals 4. And it looks like maybe over at x equals 6 we've got an unstable one, or maybe neutral. I don't know what's going on over there, so let's not worry about that one. So for example, if you've got an object starting off at x equals 2, you can use this graph to say, okay, well, if it's at x equals 2, its potential energy is 0. So if it's at x equals 2 with no kinetic energy, then its total energy is 0. It's not going to go anywhere. It's going to be trapped right at that stable equilibrium position. If we were to if an object is at this point, x equals 2, and we give the object 1 joule of kinetic energy, well, it has 0 potential, so if we give it 1 joule of kinetic, it'll have 1 joule of total energy, which means that it could go up to this position. And so if we gave it 1 joule of kinetic energy, it could oscillate back and forth, back and forth, back and forth between, I don't know, what does that look like to you? X equals 1.7 and x equals 2.4 or something, I don't know. But it would oscillate back and forth between those two positions. If an object starts off at x equals 2 and we give it, let's say, 3.5 joules of kinetic energy, well, then it's going to have 0 joules of potential again, because that's the potential energy at x equals 2, plus 3.5 means it could go all the way up to here, and it could break free of this trough that it's stuck in and make it all the way over to about here. So it would have a much wider range of motion. It would be oscillating between, what is that? Let's say x equals 5.5 and x equals, I don't know what that is, about 1.3 or so. So let's say, for example, an object starts off at x equals 4. First of all, what's its potential energy at x equals 4? Well, at x equals 4, its potential energy is 1 joule, right? So it's got 1 joule of potential just by virtue of being in that position. And then if we, for example, give it, let's say, 3 joules of kinetic energy, well, those 3 joules of kinetic energy added to the 1 joule of potential energy it has means it has 4 joules of total energy. So it could go along this curve all the way up to here. And when it gets to that point, it's got 4 joules of potential energy, so it must have 0 joules of kinetic energy. Because remember, unlike potential energy, kinetic energy can never be negative. The least kinetic energy you can ever have is 0. So once all of your total energy is bound up in potential energy, you've come to a stop. You've gone as far as you're going to go. It's not going to make it to x equals 0 with that much energy. Now, so here's my question. If the object starts off at x equals 4, how much energy would we have to give it? How much kinetic energy would we have to give it to get it all the way to x equals 0? Think about that for a second on your own. Okay, so hopefully you said 5 joules, because that's the right answer. Because remember, at x equals 4, we can see from the graph that we already have a potential energy of 1. And at x equals 0, we have a potential energy at 6. So to get from a potential energy of 1 to a potential energy of 6 is going to require 5 additional joules of energy in the form of kinetic energy. So if the object starts off at x equals 4 with 1 joule of potential and we give it 5 joules of kinetic, it'll have 6 joules of total energy, and it'll be able to get all the way to x equals 0. And I don't even know what'll happen out here. Who knows? You don't know what this graph is going to do. It might go flat. It might go up like that. It's hard to say. But it can definitely get to x equals 0 that way. Now, what confuses some people sometimes is that sometimes these graphs will dip into the negative territory. You can have negative potential energy. That's no big deal, right? In fact, some potential energies, like when we do gravitational potential energy in its more realistic form later in the year, when we talk about the potential for the force between objects, the gravitational force between objects to change as the distance changes. That potential energy is defined as entirely negative. And that's okay, because really all that really matters about potential energy isn't what it is, it's how it changes. So to go from x equals 4 to x equals 0 means that our potential energy increases by 5 joules. It doesn't really matter where we put the horizontal axis. What really matters there is the difference in potential energies between those two places. Now, since we have a potential energy curve, we could sketch a force versus position curve, and we'll do that together on Wednesday, using that idea that force is the negative of the derivative of potential energy with respect to position. So we'd have a few places we already knew. We know the force is 0 at x equals 2, at x equals 0, at x equals 3 the force is 0, at x equals 4 the force is 0. And then we could maybe estimate these slopes in through here and figure out the force that way, but I think that's something best done together. So I just need you to come to class on Wednesday with an understanding of the relationship between force and potential energy, what a potential energy curve is, what it tells you, what a point of equilibrium is, and you need to be able to identify and define the 3 different types of equilibrium. Maybe there'll be a little pop quiz to see who actually watched the video. All right, that's it. Enjoy your day off. I'm guessing most of your teachers didn't put together lessons, so I'm hoping you have some time off. That's it.